My name is Thomas Apel, and I have the pleasure to chair this session today. The Chemnitz Finite Element Symposium is a part of the DMV annual meeting this year, and this synergy leads to the possibility to have a plenary talk which fits in both the annual meeting and the Finite Element Symposium. And this plenary talk is given by Annalisa Buffa. Let me introduce her a little. Annalisa Buffa is a well-known numerical analyst. She got her PhD in 2000 under the supervision of Franco Prezzi. Then she was researcher and research director at the CNR Institute IMATI in Pavia. She was awarded an ERC starting grant in 2008 and an ERC advanced grant in 2016. Since 2016, she is professor at the EPFL in Lausanne, and in particular the head of the Laboratory of Applied and Computational Mathematics there. She was invited to give plenary lectures at many important conferences, among them the International Congress of Mathematicians in 2014. She authored and co-authored about 100 publications with almost 3,000 citations. Annalisa is interested in all aspects of numerical analysis of PDEs, among them isogeometric analysis and domain decomposition. She works with applications from elasticity, contact mechanics, and Maxwell equations. Her particular interest is in mathematical structures that need to be preserved at the discrete level. Today's lecture is about novel numerical techniques at improving the integration between geometrical modeling and numerical simulations. We are looking to a nice talk. Annalisa, please.
Okay, thank you. Thank you very much for your kind introduction, and thanks really a lot for this invitation in this hard time. It's really nice to have the possibility to interact with the community. So today I will be speaking about, say, the workflow that goes from design to numerical analysis of PDEs, of partial differential equations. And I will try to explain what mathematics can do in trying to solve a problem which is absolutely a technological problem. So this is the outline of my talk. First of all, I will describe the design through analysis workflow and giving some attention to the mathematical problems I'm interested in, and what is the technological problem that is behind my research. What are the needs, what are the answers, what are the needs, and well, the partial answers. Then one of the partial answers that exists today is called isogeometric analysis. I will devote some, will describe a little bit the essentials of isogeometric analysis and discuss the mathematical properties that underlie the success of this technique and the promises also of this technique with respect to the technological problem above. Then I will spend, say, I hope this second half of my talk by zooming a little bit on a couple of challenges that are here written in gray, just because I don't want you to read now, but it will be a couple of challenges where I try to zoom and give you an overview of the kind of techniques and the kind of mathematics we need to develop to handle, and I mean to tackle the technological problem. So the problem we want to solve are basically, I think we can look at this column on the right. In fact, we are interested in developing computational tools that are able to simulate structures of several different types. Here I've put a tire. It's a mechanical object, antennas, or waveguides. And in fact, in general, I mean, when this is my target, it means that my target are problems of classical mechanics in some sense, and I want to solve them with numerical techniques. And here I have just written a few equations that I'm interested in. So this is elasticity, possibility of incompressible limit. It can be Stokes or Navier-Stokes. Most of the time we work in, say, time-independent problem, but of course this is just a matter of applications and also taste, but in general it can be time varying. Another problem of interest is, is nonlinear mechanics, and in particular contact mechanics. This is extremely important when we try to deal with tires, of course, and the simulation of tires. And myself and my group is also pretty much interested in the development of in the design of antennas and waveguides, which has as underlying equations the systems of Maxwell equations, possibly nonlinear, possibly coupled with elasticity. So okay, we want to solve this problem, and we want to solve these problems within say a technological in a kind of a real world setting, and trying to understand in which sense we can improve the present workflow of virtual prototyping. In fact, you have to imagine that we target industrial and manufacturing engineering. We want to help and to provide the tools to manufacture engineering in order to improve and optimize their strategy of work, in fact. And what they do all the time that you are trying to manufacture a product, in fact, the first step is virtual prototyping. You try to represent this object in the computer, and the design of its geometry is done with the computer. And we also want to be able to understand its mechanical properties by suitably simulating its mechanical behavior within a computer. It means that we need to develop simulation tools simulation tools for the classical mechanics problem I just discussed in the slide before. So this is what I call the design through analysis workflow. Everything starts from the design of an object, and the design is normally done in a CAD system. And this is, I try to enter a little bit in the details on how things are constructed and what are the properties of the geometric object. In fact, in CAD systems, objects are described only via their boundaries. It's called BREP, boundary representation. And I will enter into a little bit in the details how this is done. And then the geometric model needs to be changed completely. It needs to be restarted from scratch when we want to run an analysis. So I will call analysis all what is the simulation of the mechanical behavior of a structure. And we need to build a new model. Why that? It's in fact because imagine that we are solving elasticity. We need a displacement field which is attached to every point in the geometry. So it exists also inside. And in order to do that, we need a geometric model. And in fact, the way it is constructed today with finite element techniques is that we take the boundary representation and we represent the volume with triangulation or with a mesh of tetrahedra in general. And this step requires a lot of effort, and in particular requires man intervention a lot. And we need to defeature the structure because otherwise it's too difficult to construct a mesh. And here below you see an example of defeaturing. This is a designed structure, and this is a defeatured structure where just, holes are removed, corners are sharpened. This is needed because we need to construct a tetrahedral mesh, and we can't if the structure is completely is too complex. Once we have a tetrahedral mesh, there are many tools that provide simulation of the mechanical behavior. But so I want to stress that this process happens many times within an optimization loop. So the technological problem that we need to address is the optimization of the full workflow. And in order to optimize the full workflow, it's clear that we need to work a little bit on this phase and understand if we can improve on that. And what can we do? What is the deal? How can we change the design and analysis possibly in order to reduce the impact the generation of the mesh and of indeed the construction of the geometric model. So one answer to this in this respect was isogeometric analysis. Isogeometric analysis was introduced by Tom Hughes and collaborators in 2005, and since then it has become a rather important branch of computational mechanics. And so the idea behind it, it's in fact rather simple, is that, okay, we have this problem, we want to improve the design through analysis workflow, and let's try. So let's try means let's try to solve PDEs using splines on splines geometries. I will tell you in a second what a spline is, but before that, I want to give you a framework why this was a good idea. In fact, where the idea comes from. In fact, the idea comes from the fact that splines are the very basic tools of design. In fact, every design system is based on spline computation. All the objects in free form are represented with splines. And it turns out, thanks to the isogeometric analysis, that we have also discovered in some sense again, because it was a long story, it was an old story, the use of splines in PDE approximation, we have discovered that we can actually solve PDEs in a very natural way. So it seems a good framework to start to approach the problem of optimizing the design through analysis workflow. So here is the description, a very quick description of what a spline is. You have the segment 0, 1, and you split in pieces, and these are the pieces, and then you construct a piecewise linear function on these pieces that are the BI0, and then you apply the Cox-de-Boer formula, which is this one that basically does degree elevation, and what you obtain is a space of splines that are piecewise polynomials of degree p and regularity up to p minus 1 at the knots. Okay, these are called knots. So you have regularity p minus 1 at the knots. If the knot is repeated, the regularity is lower. So it's a pretty flexible way to represent piecewise polynomials that have a global regularity in some sense. And the way they are used in design is very shortly represented here. The blue line is what is called a free-form geometry, and it's just described with a polynomial. The polynomial are the red dots, are the control points, and the blue curve is just a regular curve that sits close to the polynomial, and the blue curve is the spline, and the red dots are the control points, and the polygon is called control polygon. In this way, the geometry can be moved by moving control points, and we can actually define many geometries like that. And of course, everything can be tensorized. The splines are defined in 1D, and then they are tensorized. And here we go. We have a definition of splines. We can say what a spline geometry is, and then define spline methods for PDEs. So I have a parameter space that I call omega hat, and I have a computational domain that I call omega. And omega is a spline geometry if there is a spline mapping, capital F, that map the parameter space into the physical space. So the pipe is my physical space, and functions, approximation functions for the unknown of the PDE are just constructed by mapping spline from the parameter space to the physical space. So this is extremely straightforward. And of course, it may be that the geometry is defined at a coarse level, and I need much more functions to be representable on the physical domain. Then in order to obtain that, I can perform knot insertion and degree elevation in order to obtain a richer representation for the unknowns of the PDEs on the physical space. So I think it's, okay, this is maybe hidden here, but here it is written, actually the stability of these algorithms of knot insertion and degree elevation are the very basic reasons why splines are a tool in design, because it represents free-form surfaces that can be refined selectively and in a very stable way. So splines turns out to have an incredibly nice mathematical structures, and of course, nice mathematical structure generates powerful numerical methods. And that's what we have, in fact. We have powerful numerical methods. We have powerful numerical methods. We can, we have optimal approximation properties. So if we have any function u, which is regular enough, we can project on the space of mapped splines, and we get an optimal approximation estimate like this one, where where the lack of locality of splines plays a little bit against the estimate, because q prime is actually the big is the blue square, and Q is the small square here in the middle, but still this is a local estimate, and it works pretty nice. I mean, allows us to develop numerical methods. In fact, we can even have local refinement. Splines can be defined in a hierarchical way over hierarchical meshes, like this one that you see here, for example. And here I'm showing two simulations. This is a shell simulation with a point load in the middle, where you see that the space has been refined to deal with the locality of the data. And this is the von Mises stress of a large deformation problem, where the structure undergoes a pressure from above. So it's a nice mathematical structure. This means that we can do a lot. And in fact, we can solve nonlinear solid mechanics problem. We can solve electromagnetic problems. We can also very effectively solve fluid dynamics problem. So the story seems nice. There are a lot of techniques we can put in place to have spline methodologies over spline geometries. But now that a lot of work has been done, I want to do a step back and understand if I did tackle my technological problem at the end of the day or not. And so this was the technological problem, bringing design close to analysis. So I want to know if I did solve it or not. And okay, let's go back then to what it was. It was that in design, the volumes were described by B-reps and not by spline geometries, but by boundary representation. And by the way, now I enter a little bit into the details of what is a boundary representation. A boundary representation means a bunch of spline surfaces, like this one, for example, that should represent a boundary. Okay, this sounds still reasonable, but in fact, union, intersection, and in general Boolean operations are allowed and are supported as a boundary representation. It means that my boundary is not represented as a nice collection of B-spline manifold, but is actually represented by chops of B-spline manifolds, like this one, which is cut. So this one is just cut along this line, and I have a lot of these pieces that comes together and that are just put together with topological information. The model is not even watertight in general. It's never watertight. I have pieces of a spline manifold that are put one beside the other via topological information only. So I know what is close to what, and this is it. So the truth is that B-reps are not spline geometries, are very far from being spline geometries. So in some sense, we have developed nice methods with the idea that they could be useful, and now we have to ask ourselves in which sense would they be useful. And in fact they are, but we need to understand what next development that we need to do. And at least this is the next development I tried to do in the last few years. And so my idea was to really try to work hand in hand with innovative approaches in design. So clearly B-rep are not enough, and fortunately enough, they are not enough not only for analysis, but in general, they are not enough in the today technological world to provide tools for design. And there has been a very important effort in the recent years to define, instead of BREP, what is called VREP, volumetric representations. And this is an effort that basically is done in Technion in IFA. And the main motive is not really analysis, but the main motive is additive manufacturing, because they need to provide the tools, design tools for additive manufacturing. And in order to do that, they need to represent volumes. So representing volumes means just that if this is my geometry, I also have a volume inside, and I don't have only the boundaries. I also have the volume inside, and union, intersection, subtraction is still allowed. So you see that a generic geometry is an object like that, where the structure, when I can put several pieces together, I can cut them, and I can manipulate them. In general, what will happen is called that the geometry are, the general name for this set of operation is trimming. It's when you take a geometry and you just cut a piece of it, and you have a new geometry, which is just the one before without the piece. So what we do is that we try to do the same. We try to take volumetric representation that is not a valid geometric model for PDEs, but it's a collection of volumes that are treated, that are put together via Boolean operation, and we want to solve PDEs on such a geometry. So what is that? What is the program that we have and that we develop? So we developed the program of constructing methods on VREP, and of course we want to develop mathematics because we want the solution to be certified. And at the end of the day, we also need to deal a lot, and it's a big lot, with linear algebra, because of course the structure that we deal with can be extremely complex and extremely big. So we need to make sure that all what we do can then actually transform into a linear system that is suitably solvable. So this is the change of paradigm. We try to design methods that can solve problems on VREP. So, and this brings me to the challenges and to some of the solutions that I want to address. So the first one, and here I'm entering a little bit into the technical part of my talk. So the first problem I want to address is how we deal with Boolean operations. And the second one will be analysis-aware defeaturing, and understand how defeaturing geometries can impact the accuracy of analysis, and how this can be, controlled. So let me start with the geometry as results of Boolean operations. Okay, here I have three geometries. And I imagine that, so I go to the toy problem that I can solve with mathematics, and for which I can develop mathematical methods that then can be used on less toy problem. So here I have a geometry that is done of three pieces, and I assume they are put one on top of the other. And I assume that I have one simple way is to assume that I have a hierarchy in this construction, and that I have a domain below that is called omega 0, and then there is omega 1, and then there is omega 2, so that it's one on top of the other with a given hierarchy. And say the further domains are called with a star, and you see that omega 0 is just omega 0 star minus all the part that I removed. So in general, elements are cut, and you see that several elements of omega 0 are cut by the ones that come on top. I have also, I need also to name the interfaces. So for example, this interface will be, no, not this one. Okay. So for example, this is gamma 2, 0 is the interface between omega 2 and omega 0. Okay, so the idea of how can I deal with that, I deal with that. I am proposing this technical slide where I just try to say how I deal with that. In fact, I will define, imagine that I'm solving the Laplace problem. In general, I can be solving any elliptic problem at this stage. So I set my equation in each of the domain, and then I set transmission conditions at the interfaces, as I would do in any, in any similar situation. I have 3 interfaces and I set 3 transmission conditions. Then, of course, all the time, I will also have to carry with me boundary conditions at the boundary of the full domain, but I'm not going to detail that. I'm just going to understand and describe how I deal with the interfaces. So the idea is to use a Nietzsche method. A Nietzsche method is just, it's a very well-known technique in finite element theory, and it means that we are just solving, say, a variational problem where the bilinear form that I want to assemble looks like that, where I have the Dirichlet integral, the grad U, grad V integral representing the Laplace in each subdomain. And then the 2 interface conditions are taken into account basically via a penalty approach, where beta is a penalty parameter. This is the size of the mesh at the interface, and these are the jump of the U and the V. And these are the Nietzsche integrals which I need in order for my method to be nice and converging. I'm not going to enter into the details of that. I just want to say that this is exactly what we do. And so the way I solve it is that I instead of the solution UI, I will have a solution UH, which is just constructed via mapped splines of degree P in each patch or in each domain. And this object here is, I can choose that. It is either the average of the normal derivative, or it is the normal derivative on one side. In fact, it turns out that I need to elaborate further on that in order for the method to be stable. This quantity is it has to be chosen properly. So it is either the flux. So imagine that I am computing on this interface. So this quantity is either the normal derivative computed from the element above and not from the element below, because I need a stable strategy to compute fluxes. And if I don't have a good element above, I will need to do some stabilization. So in general, on very generic, so the message that I want to pass is that on very generic Boolean geometries, it may be that the Nietzsche formulation that used to be known as very stable for finite elements fail stability because of the fact that the elements are cut, and so they can be very, the shape of the elements can be very, very strange, and the method may fail to be stable. And in case it fails, we need to stabilize it. So we have optimal accuracy of this technique for Laplace and linear elasticity. And here I just want to show one numerical example where you see that I have a geometry which is composed of 4 pieces. And here I'm solving, it's an academic problem. I'm solving with a pre-computed, it's an analytic solution. And here you see my convergence graph, where if I solve with the quadratic splines, I get quadratic convergence in H1. If I solve with the cubic splines, I get cubic convergence. Quartic, I get convergence of order 4. But I want to stress something. There are a number of problems that I need to solve in order to obtain this kind of estimates. And in fact, first I I want to show you exactly which kind of algorithm I need to set. Because algorithmically, the problem is not easy at all. So at each, oops, I'm sorry. Okay, it's very delicate. At each interface, imagine that it's this interface. At each interface, I have two spline surfaces that get in touch one to the other. And I need to compute, first I need to compute fluxes. Then I need to compute interface integrals. It means that on this interface, I need to compute an integral of blue functions against orange functions. And I also need to compute integrals on the cut elements. So I need to compute integrals on this interface. And I need to compute integrals on this element, for example. And as simple as it seems, computing integrals, it's a very expensive, computationally very expensive, and is also very prone to mistakes in the sense of round of errors and so on. We really need to be careful when we compute integrals to the precision that we use. And in fact, so what I need for the interface integrals, I need to actually, oops, I'm sorry. It's not easy to use my system here, sorry. So I need to make sure that I construct a mesh of the interface that guarantees the accuracy of the integral. And then I had also the integral on this element. In fact, I need to construct an integration rule on this element. And the only way I have to construct an integration rule is by subdivision. So I'm again back to meshing in some sense, because I need to construct a mesh of this element. And this is one strategy to construct the mesh, but every time I have to do that because I need to compute integrals over cut elements in a precise way. So this requires again meshing, but it requires meshing on a local level, because for every cut element, I will need some meshing tools. But this is much less generic than, I mean, it's a very specific mesh problem that I have and that I can try to address with a specific tool in order to avoid, you know, going back to the problem that I had at the beginning of constructing meshes for a complex object. So, of course, this is a real challenge when it goes to 3D problems. Is a math and a coding challenge, I would say. So when we go to 3D problems, we need to face the fact that we cannot mesh a generic object. We need to face the fact that the intersection of two spline surfaces can be a very complex object, which is extremely unstable to compute. So here I'm just kind of trying to propose a 3D. So we did run a 3-dimensional problems, rather complex one. So the one that you see here is actually it's a mock mold where we try to design the cooling channel so it's a mold. It's an object like this where we're trying to design the cooling channel inside in order to so the cooling channel inside, with the idea that the mold can be 3D printed and the cooling channel can be designed in a very general setting. So this is the kind of mesh that we use. So you see that the cooling channel is much smaller than the underlying mesh that we use to solve the problem. And in general, what is that we need to do? We need to construct local meshes of objects like the yellow one. And we do it via hybrid high-order mesh. Basically, we construct hybrid high-order meshes for integration, and we drive our construction with the mathematical understanding of the error that we are committing. And this is the kind of estimate we can hope to have. So we have that the error between the exact solution and the discrete solution computed with the integration. It goes actually as So I have an approximation error that depends on the degree of the spline and on the mesh size of the spline mesh, which is the yellow one, this one. And then I have another source of error, which comes from the integration that I need to tune, because this integration costs me a lot of energy, and it is exactly the place where human intervention may be needed, because I need to construct the mesh, and the mesh can fail. And in fact, it does fail many, many times. So I need to tune with my analysis, with my mathematical theory, what is the least I have to do in order to have an accurate method. And in fact, okay, so I have to remove that. So here is what you find. You have that if H is the size of the sub mesh that you have in here, then Q is the degree of the boundary approximation. So I have this piece of a circle, and I need to approximate it with a polynomial of degree Q. And and this is the kind of estimate that I obtain. So you see that either I pay a very small sub mesh, and then in this case, I can allow myself a less accurate approximation of the boundary of the sub mesh in order to equilibrate the errors. Or if I decide that I take the sub mesh as coarse as possible, then I know that I will have to pay a good approximation of the boundary of the object in order to keep the error balanced. So again, this is not really, I mean, for me, it's not really a matter of designing an optimal strategy. It's mostly a matter of balancing errors and trying to design a robust strategy. Because as soon as you take an element like this and you start telling yourself that you want a degree 4 approximation of the boundary, you immediately run into troubles, because it's very difficult to have robust techniques that works for high order polynomials. So this is the situation. This is where we stand. This is the kind of algorithms that we try to construct, and then we also apply them to in various settings. And for example, one of the setting is a shell theory. So exactly the same, say the same framework I proposed just before can be applied to shell theory. Oops, I'm sorry. This is what is called a Scorgheris-Leroux shell. It's a very typical test for shell where we have a point load here, and these holes are constructed by trimming, so by intersection with actually with the infinite cylinder on the vertical side. And here actually we also run an adaptive approach on top of our method. And you see that actually, okay, I don't want to detail that a lot, but this is just to show that our way to deal with unions and Boolean operations in general can be coupled together with other existing techniques like hierarchical refinement of meshes, and of course everything should be worked out in order for the adaptive strategies to take into account the Boolean operations and so on. This is another example where we apply our strategy to an industrial problem. This is the B pillar of a car submitted to a point load. So all the shells are submitted to point loads, which is not something we like a lot as mathematicians, but that's life. And again, the holes are treated by intersection, and definitely, I mean, our technique is robust enough to be able to be coupled with a hierarchical approach and solve the deformation of the B pillar in a very, very accurate way. So the summary is that here is where we are. We have an optimal method for Laplace and linear elasticity. It is based on Nietzsche approaches. So this means that it requires the computation of fluxes, the computation of interface integrals, and the integrals over cut elements. This is a challenge in 3D. Okay, I'm starting from the bottom. This is a real challenge in 3D. And of course, my question is whether can math help in designing robust strategy. For example, when we try to compute spline-spline intersection, there are many steps in the algorithm that fail to be robust, and we need to understand why and to improve on the robustness. And then, of course, there are other things that comes to, I mean, there are other challenges that would be very interesting. One challenge that, oops, I'm sorry, that is maybe not completely say understandable from the mathematical point of view is that when you try to go to the engineering community and say, hey, look, this is my method, look at how nice it is, then they will immediately tell you, but I don't want to compute fluxes. I don't want to compute Nietzsche integrals. So can we remove them? That's really a challenge. And why do we want to remove them? Because in general, the simulation is non-linear, and if we, as soon as we add the terms in our problem, then we need to differentiate those terms, and the differentiation may be hard because we need to compute, because we need to put our method within a non-linear solver. So this is definitely a challenge. Can we define unions and intersection without Nietzsche integrals? And of course, then the other issue would be the extensions to nearly incompressible materials or to vector fields problem like electromagnetics for the design of waveguides. So now in the last 10 minutes or so, I want to go to my second challenge. It's zooming on a second interesting point, and which is analysis aware defeaturing. So let me go back to the picture I showed at the beginning. This was the picture of defeaturing where I had the geometry, and this is defeatured. Holes are removed, angles, well, corners are sharp and so on. Okay, and then this is the geometry that is given to the solver. We have no trace of the fact that there were holes and that the corners were sharpened, there was what is called the fillet, so the corners were without sharpened edges. So the question is, how can we understand the impact of defeaturing in the accuracy of the numerical technique for PDEs? And this is in some sense important because defeaturing is a relevant part of the meshing step. In order to mesh, we need defeaturing. But if we avoid meshing, maybe we don't need defeaturing, or if we defeature, we want to know what is the impact of defeaturing, and we want to understand if we can measure this impact. Actually, defeaturing takes place in many different contexts. One is really about geometric details. There are also other defeaturing techniques that are, for example, this one, thickness is removed. And instead of having a solid, I get a collection of surfaces to compute my PDEs with. And I can ask myself whether the thickness was important and to which extent I did right or wrong in using only surfaces, so say reduced dimension models. So the ground rule that we try to apply in this part is that we don't want to make a computation on the full geometry. I mean, the geometry, the full feature geometry is out of my scope. I cannot reach it. I cannot compute on that. But can I still get some information of what would be the impact of features on my solution? So, okay, I need to remove that. So, okay, maybe I can skip, it's written in the next slide, so because I don't want to be late, so I will go here. So this is the toy problem that I propose to look at. Okay, this was, okay, I have a D-feature geometry that is omega 0, and I have a geometry full of features that I call omega. And so the idea is that I want to compute only U0, that is the solution on omega 0. I don't want to compute anything on the omega. So all the computation on this domain is out of reach for me. I compute only U0, and I want to know how wrong U0 is. So that's the idea. And how do I do that? Well, I would like to understand a posteriori what is the impact of all these details that I have here and that I didn't take into account. But I don't want to allow, so what do I allow myself in terms of computational effort? Well, I want to allow myself, it is written here, evaluation of U0 only, that's the important thing, on the blue and red lines that you see here, okay? The blue and the red details. Well, of course, just as a matter of fact, U0 is not defined on the red lines, that's why they are red. And I need to construct an easy extension of U0 and to evaluate their easy extension. Okay, so I need a representation of the error. And this is the representation that we found. It is basically a residual-based representation of the error, which I just present like that. So G is the Neumann data that is included in the Neumann boundary condition I did not describe. And this is the normal flux of the defeatured solution, okay? So this is on the negative, the pictures that you have here below are the ones that correspond to these formulas. So imagine that I have one negative feature like that. Then the representation of the error will be on the curve. So I compute the solution U0 on the square, and I allow myself evaluation of fluxes on the green surface. This is the flux that I evaluate on the green surface, and I also have the Neumann datum that I had, that I had on the green surface. So this is the one, I mean, this is my representation of the error. And when the detail is positive, so when the detail is red, like in this case, then it's a little bit more complicated. And what I do is that I construct what is called in geometry bounding box of the detail. So this is the bounding box. I don't want to solve anything in the detail itself because it's maybe complex, but I solve on a bounding box, and then I have another representation of the error. When I have many details, the representation sum up. And this is what I get at the end. So for every negative details, I have a piece of the representation. For every positive detail, I have other pieces. I mean, I have all these guys. And we have a theory that says that this is more or less what we obtain. So the error, it's bounded from above and from below up to constants by my representation of the error. So it seems that this tells me that in some sense, up to constants, so to say, my error, my a posteriori representation of the error is correct, because actually it's an upper bound and a lower bound up to oscillation of the error itself. So of course this is done for the Laplace, and actually this we have only for the Laplace, and it requires extension in many directions. We want to use it for elasticity, incompressible materials, thin structures that are really a topic, a very important topic in computational mechanics. We would like to avoid the use of fluxes if possible. Still, here I use a lot of flux computation, and if I want to avoid the computation of fluxes, I need to change it. And I would like also to treat other kind of modeling errors into the same mathematical framework. But okay, these are the challenges for the future. Now, before concluding, I would like just to give a numerical example. So very often we have structures with holes. Okay, this is it's an academic problem again. So what happens if I remove all the holes? The holes are gone. Then I compute a solution on the square. I get a rather big error. I get 50% error if I do that. Then my estimator here is telling me that when the gradient of the solution is steep, I mean, when the solution is steep, the gradient is big, then the error is bigger. The error due to defeaturing is bigger. And in fact, you see that the error indicator tells me which details are more important than others. And in fact, it tells me that the details that are more important are the one close to the steep, to the place where the solution is steep. And in fact, the first details that the estimator tells me to insert are the ones that are here, are this one. And if I do that, I get to a 10% error, which most of the time is largely enough for a computation. So I get a 10% error just introducing 7 small holes in my simulation. And so it's, if I want to go to a 1% error, I need to make a rather larger effort, because I need to insert all these holes in my geometry. And of course, you have to think that I need to mesh it. Every time I need to construct a suitable mesh for that. So it's not trivial. I would love to avoid holes, but the featuring has a price, and that's the price. Actually, I also have a picture showing how the estimator is a good measure of the error itself. Here you see, so here I'm inserting holes one after the other, following what the estimator tells me which detail is more important, and I insert one after the other the details, and you see that the error goes down, and of course it goes to basically, it goes down when I have inserted all my details. And this is the estimator above that estimates the impact of each detail. And you see that the two are extremely nicely parallel. And this meaning that my estimator is actually a very good estimator of the impact of the featuring. So there is a sentence here below, okay? So the message here is that for once, we can look at what is the impact of the featuring in analysis. And in fact, there is an impact, because clearly in this very simple geometry, in order to get an error that is 10%, we need to introduce a small number of holes. But in order to get an error that is 1%, we need basically all the details in the geometry itself. So it's important to drive the featuring with analysis. At the moment, it's not at all like this in the general, in the general framework that is used when an object is designed. The featuring is done a priori, before analysis, before everything. And instead, analysis really matters, and I think should be taken into account. So I want to conclude here, and I would like to thank you very much for your attention, and I need to acknowledge my sponsors that are at the bottom of the page. Thank you very much.
Oh, thank you very much for this nice talk. So we have seen the impact of mathematics, the impact that mathematics can have. This is very nice. Yeah, questions. In the questions and answer section, we have two questions from anonymous people.
Okay.
The first one is on slide 9, the blue spline with the red control points shows a kink. Is this really representable with the spline?
What is the slide? Okay, 9. I have 9.
Slide 9.
Yeah, I need to go back. Yeah, so it is representable. Oops. Well, I am terrible with, okay. It is representable if the point here is repeated twice. Because here I don't have strict signs. They can be also equal. And in fact, across a knot, the spline is P minus 1 regular if there is only one repetition, but it gets P minus 2 regular if the knot is repeated twice, and so on, up to this continues if the knot is repeated P plus 1 time.
Yeah.
I hope I answered.
Yeah, I would think so, yes.
Okay.
And the second question is on slide 29 or 30.
Okay, let me see if I can, oops. I'm trying to get my, okay, I do like that.
So and the question is, why is adaptive refinement with P equal to 4 less accurate for low degrees of freedom? For a smaller number of degrees of freedom, probably.
Here then.
Yes, I think so. That.
Okay, so this is just, I mean, this was, I put this slide just with the idea of showing that that actually we are interested in shells and in coupling everything with adaptivity, because in case of splines, it is very important. We are constrained with the tensor product mesh. And so this is just, I mean, P equal 4 is always below, okay, no, here is above.
It's above, yeah.
Okay, well, this, okay, so, but this is with no, these curves are the ones with no, with uniform refinement. So it's submitted to a point load. And that's what, of course, I have no, there is no reason why P4 should be better than P3. P equal 4 should be better than P equal 3 because the solution is singular. The mesh is refined in a uniform way. And in fact, it happens that P equal 4 is less accurate than P equal 3. They are, the curve, I mean, the only thing I know from the theory is that the two curves are parallel. And in fact, they are parallel because the slope depends on the sublet space where the solution belongs. There is no reason to believe that P equal 4 should be better than P equal 3. And in general, it's not in this kind of problem. So raising the degree, we are doing splines. So when I raise the degree, I also raise the continuity of the functions. And in general, this can be not so good when I'm actually looking for a very singular solution.
So thank you. I think it answers. Maybe the anonymous guy could write something or raise the hand.
I don't see either ends, nothing, huh? It's, you see it,
yeah.
I don't, okay.
No, I don't see any.
Okay, anyway.
Are there further questions? Yeah, if this is not the case.
There's a raised hand.
Where?
Marietta Ehret. I'll allow her to talk. Please, you have the microphone.
Yes, I want to ask a question. If I have a geometry with optimal elasticity properties, as in this slide here maybe, and then I take a refinement at the curved parts, as you see here, and then and if I then print this in 3D, then I think that the mass changes and also the elasticity properties. Do you have some experience with this connection to 3D printing?
I am sorry, I'm not sure I understood. So the elastic properties of the object does not change when I refine my mesh. I'm just changing the level of accuracy that I use to approximate the solution of the elastic problem.
I think if I print it in 3D printing,
in
then
3D
the mass,
printing.
yes,
Okay.
then the mass changes if you refine the mesh.
No, so it's not, no, because in 3D printing, so what do you mean that I use my, so I'm not simulating the 3D printing phenomenon here. I'm just simulating the structure in itself. Okay. Of course, if I want to, so this is not at all a mesh. It's not at all a mesh on which I would print, but it's just a simulation. It's just a mesh on which I simulate the behavior of the structure already printed. The simulation of the printing process is something that is completely different, and it requires. I mean, it's not the elastic model of the structure that enters into play, but it is the modeling of the printing process and the way the printing process may generate stresses or, I mean, may generate pre-stress inside in the structures and, oh, I'm sorry, in the structures and so on. But this is not what I'm doing here. I don't see. I don't know if I answered. If not, I'm sorry.
So thank you for the answer. And are there further questions? Please use the raise hand function. if this is not the case, I think we should thank Annalisa again for this nice talk.
Thank you. Thank you very much.
So, and I close the session. Thank you.
Okay, thank you.